So next is the linear space, and we will talk about autoencoder and some complex problems if you use neural network. So the first one is autoencoder. Of course, I provide several different examples right here from Keras, same as TensorFlow. Okay, so basically you can just take a look at these autoencoders. They have codes, they have explanation if you don't follow what I'm talking about right here. So of course that's a little bit complex. I will use some simple way to explain what is autoencoder. And I think one of the good way to understand autoencoder is like this. You Google autoencoder and you take a look at the pictures that found by Google. Okay, you can see that there are several different network data structures. They all describe what is an autoencoder. So I will pick some of them to explain it. So right here, I have two pictures. So basically, when we talk about learning, we have a very specific task like regression, right? So there are several things we have to do before we start autoencoder. Okay, usually one is supervised, the other is unsupervised. So for supervised problems, that is quite easy. We have a model, right? The model describes the relationship between your input features and your result, which is your target, y. But sometimes we don't have such kind of very specific, very explicit problems. You have a feature, you have a target. Can we write it again? Features and we have a target. However, sometimes, okay, we don't have specific, we don't have implicit y. What does that mean? That means we just have a lot of data. We have no implicit target y. We simply just have some features about the data. What kind of application like this? For example, clustering. I have several data, n data. I would like to know what is the distance between data point. And for the other data point right here, I would like to know what is the distance between these two data points. Because if I have such kind of information, I can draw it in the space. For example, your surface, like this. So if data point 1 is right here, for example, a P1, data point 1, data point 2, P2 is right here, and I have another data point right here, something like that. I can cluster different data points in a space. So the most important things of unsupervised learning is to define how did you define the distance between two data points. So that is unsupervised learning. However, the other important unsupervised application is what we call autoencoder representation. If you collect a lot of data from, for example, from the real world, usually we will have two features, and we don't know which feature is more important than the other one. So the rule of thumb is that if possible, you will try to collect as many features as possible at the first place, and then we do analysis, try to figure out which feature is more important and which feature is not that important. So here is how we do such kind of analysis. One, we have taught you how to do this by using PCA, right? Principal component analysis. We do dimension reduction. What does that mean? Here we have the original space. It has m dimension, right? So after we do principal component analysis, we can shrink the dimension from m dimension to another, for example, k dimension, from m to k dimension. What is the mathematical tool we use? Okay, I have introduced before. We use eigenvector and eigenvalue. That is the original space, right? Original space. The original space has m dimension, and the new space has only k dimension. So that is called dimension reduction. Okay. We also call it latency space. In Mandarin, okay, we use a very strange word to describe such kind of space. 中文叫做潜在空间。比如说，我们会有一个圆空间。然后呢，我们会用 PCA 的方式，我们还记得 PCA 嘛，对不对？我们就是教你怎么做variance， 对不对？我们在空间中做平移、转换视角，然后把它压缩到一个 K 空间里面。K 空间后面的东西呢，因为 variance 太少了，所以我们就选择性的把它丢弃掉，所以我们只留下前 K 空间。那前 K 空间可能已经包含了足够多的 variance， 比如说80%或90%，这个我们之前上课有讲过了。 那新的这个空间，我们一般嘴巴讲就叫新空间就可以了，好，但是它实际上有个名字，它叫做潜在的空间，是叫 latent space. So that is how DCA works. However, trying to do such kind of dimension reduction, okay, and the principal component only consider the variance, right? We were talking about before, only consider how many or how much variance has been kept in the new k-dimension space. And of course, if we have more variance being kept in the new space, the more the better. So that I can describe the original data by using another k features or dimensions. That would be more efficient. Is there any other way to do such kind of principal component analysis? Yes, the other one is called Auto Encoder. We have neural network, right? So the neural network like this. Okay, we have these. For example, originally, okay, I have 6 dimensions to represent my data, x1 to x6, so that is my input layer, right? And I would like to make some space transformation. I would like to use another, for example, k dimension to represent this data. The basic idea is like this. We set up a hidden layer right here. So for example, hidden 1, hidden 2, and hidden 3. For example, we have a hidden layer and 3 neurons right here. A equals 3. The autoencoder is like that. We have 2 structures. Okay, the first one is called encoder, and the other part right here is called decoder. We send information from the left-hand side to the hidden layer and to the output side. But originally, at the right-hand side, this should be Y. But we don't have Y right here. So the most important thing is right here. At the end of the decoder, okay, I have a neuron right here. X1 prime, 2 prime, 3 prime, X4, X5. And we connect it. We have weights right here. So basically I'm writing this way. X1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And of course, it is fully connected. So we have another different weights. I use another light green right here. And have different weights. Okay, there's another color right here and then lighter. Okay, just make sure you understand we fully connected the first part, which is the encoder, right? So it seems like that we transform the original data from a 6-dimension space, which is x1 to x6, to another space, and this space has only 3 dimensions because I can represent the original data, which is a 6-dimension, by using only 3 real numbers, and they are 3 dimensions. And the most important part is right here. After I map the original data from the 6-dimension to the 3-dimension space, then I do decoder, which is recover the information like this. So that is, we form a very, very basic neural network that represent how do we transform the original data, which is in a 6-dimension space, to a 3-dimension space, represented by the hidden layer. And then we further transform the data in the 3-dimension space back to the 6-dimension. So how do we design the loss function right here? The loss function of the autoencoder, okay, sometimes we use AE, okay, to represent the autoencoder. It's very similar to MSE, which is mean square error. So it's the same. We have a lot of data, and we summation them, and we try to do square error, right? But right here, the square error is like this. What we would like to minimize? We would like to minimize, okay, if I have an input data, and I input them on the left-hand side, and it will map to a smaller dimension, which is represented by H. And then the decoder has a lot of weight. They will recover such kind of mapping to remap information from 3 dimension to 6 dimension. The loss function I designed, the auto encoder designs right here is that the output, which is the recovered data, is as similar as possible as the original input, which is X. The output is X prime. So we minimize the mean square error, but we don't use Y because we don't have Y here. So we use the output as X prime. We would like to use such kind of neural network to help us to map the data from the higher dimension to the lower dimension, and back to use the decoder to map the dimension from the lower dimension to the higher dimension. That is the most important things is right here. We don't have y, so it is an unsupervised learning. And the most important of all is that if we have a lot of data, for example, with n data points, so we feed the data point into the loss function, right? So the weights right here, x, right? X prime is we have original x and we have weights right here, right? And we pass it through an activation function, so that is h, right? So then the x prime is that we have an activation function here, we have h right here, and we have another new weights right here. 这看懂2层嘛，对不对？从前面那一层是原本的资料是大 x， 然后你乘上前面的 weight， 前面就假设这个是 weight， 好，后面这个我们就假设是 weight prime， 好不好？那前面是个矩阵嘛，好，6层的矩阵，然后乘上一个 weight 是 w 嘛，好，红色 w， 它就变，然后再过 activation function， 它就变成 h 嘛。H 再经过后面这个 decoder 之后，乘上了另外一个 weight， 好，所以这个 weight 应该是 w prime， 但是 w prime 再过应该会有 activation function， 好了，就是我们会让这个 x 跟 x prime 要尽量的靠近，好，所以上面那个 loss function 是他们的差嘛，差的平方和均方差要越小越好，越小越好就表示说你随便丢一个资料进来，好，6个维度的资料进来，好，经过了 w 到 h， 然后从 h 再 w prime 到 x prime。X prime 跟 h 要 X prime 跟 x 要越像越好，那越像越好，表示说它能够还原。那原本6维的资料，现在就这样子，好像中间3维就可以容纳所有的 information 的，因为它可以 recover 嘛，对不对？对，所以这是 Auto Encoder， 所以它就为什么叫做 encoder？ 那为什么叫 auto 呢？我的猜想是因为说这是一个 unsupervised learning 嘛，对不对？所以我们没有 y 嘛，就是中文好像发音很怪，叫自动所以这个结构是长这样子。Okay, so that is the structure of Auto Encoder. Take a look at this hidden layer. So since the hidden layer is constructed by the original features with some weight and with some activation function, okay, so this is another space. So basically that is the space as well. We can use the latent space to represent the original data very well. Why very well? Because we can use the latent space information to reconstruct the original space, which is x prime, right? So basically, the latent space right here is very, very similar to principal component analysis, the k dimension. So we can use this structure to compress the original data from 6 dimension to 3 dimension. Okay, that is the idea of latent space. If you have data, okay, you have a data table like this, and you have tons of features from 1 to n, right? But you don't want to deal with such kind of n dimension. So before you do so, you may sample some data. For example, you have n data. Okay, you can send some of data and construct an autoencoder like this. Right here, maybe I can shrink the dimension from the original n space to a smaller k space and reconstruct it. So basically, we can use the encoder part, which is the left-hand side part, in preprocessing, so that the original data will be converted to a smaller space, and we guarantee such kind of mapping, such kind of transformation, such kind of latent space can well represent the original data. So we can apply different, for example, classification, different algorithms, different whatever things. Apply them on the latent space, not the original space. 好，中间再讲一遍啊。所以如果你有个资料，然后你的 M dimension 实在是太大，比如几千几万、几亿都有可能，因为你随便收集资料，你根本就不知道哪个是重要的啊。所以你可以用 PCA 的方式，我们把重要的资料，所谓重要的资料就是 variance 大的资料，把它留在前 K 的那边，对不对？好，这是传统的做法，这是数学解嘛，用eigenvalue、eigenvector。那你也可以创造一个下面这样 Auto Encoder 的 neural network 的结构，对不对？然后呢，你的目的当然是说，它这中间这个 K dimension 这个 hidden layer 可以很准确的把原本的 M dimension map 到 K dimension， 然后再还原到同样 M dimension 的资料上，所以它似乎可以跟 PCA 一样做一个压缩，或是叫 dimension reduction 的动作，对不对？所以原本你有几千几万个 dimension 在原本那个 M 维面，那你中间可以适当的设计，比如说 K 设计成1000维啊、500维啊、300维啊都可以，然后你把资料你就设计一个这样的东西，然后你去原本的 n 笔资料里面，比如说抽一些样出来，或者说那 n 如果没有太大化，就做一个这样的 training， 把那些 weight 啊，就是中间那些 weight 全部都 train 出来。 那当你到实战的实用的时候呢，你不要把原本的 m dimension 的东西全部拿去做，比如说我们要后面要做一个，比如说 SVM 啊、classify 啊，甚至像这个 classify 的，你反而是用中间的那个 k 维的资料当做 input data 输入给其他的，比如说 SVM 啊，或者是我们前面讲的 equation， 因为我们相信这个 Auto Encoder 的前面的 encoder 跟 decoder 的结构，只要你那个后面那个 loss function 够低的话，表示中间的 k 维其实可以非常好准确的表示原空间的字，它把塞在 k 维里。那既然这个 k 维这么好用，那我就不要用原资料，因为原资料可能太大了，比如前面有1000维，那这个 k 维可能只有55维、80维，所以呢资料量就变少。资料量变少，你记忆体啊 storage 就会好很多。那你后面等一下做，比如说做 SVM 啊，或做任何我们前面教过的 classify， 你就会电脑不是你轻松很多啊，电脑会轻松很多。好，所以我们是坚信中间的这个 lane space， 然后中间这个东西叫 lane space。我们用 auto encoder 的目的，并不是要用它后面的那个 x prime， 我们是从 x train through x prime 的过程当中，中间一定会有一个比较小的维度，我们是要用这个维度。所以当你在 train 好这个 auto encoder 之后啊，其实你不是去拿 x prime 出来用，你是把原资料从 m 维变成 k 维之后，你是用中间这个 k 维的资料去表示原资料。然后你就看后面要干嘛吧，你就拿这个 k 维资料去跑。所以有很多时候我们会用 Auto Encoder 或是 PCA 在做所谓的前，就把资料压在下面，后面再运算，好吗？好，但是 Auto Encoder 不是没有缺陷，我要用英文讲哈。So that is Auto Encoder. However, using Auto Encoder as a part of the analysis procedure in preprocessing. However, Auto Encoder is not always that useful. There are several different things you have to consider. First, how many dimensions you have to set in the hidden layer? That might be a try and error process. So that, for example, you have, for example, right here, I have 6 dimensions right here, right, originally, and I set a 3-dimension hidden layer, okay, as a linear space dimension. I think that can be good enough because we have enough space to contain the original data. So the original data will be mapped to the new space, new linear space, and all the data points still we can distinguish every single original data point in the new linear space. It is simply just as what we consider in PCA. If your PCA has very few dimensions in PCA, okay, the total variance will be lower, right? We talked about it before. So if you only kept a very few dimension in PCA, then that means you lost a lot of information, a lot of variance from dimension k+1 to k+2 to n, right? If you lost too much information, then your linear space may not be able to represent the original data, so that we cannot distinguish data point in the original space, right? We cannot distinguish the data point in the new linear space. So the situation is exactly the same right here. If you have to fill hidden node right here, so that the hidden node, the space, the new linear space, may not be able to represent the original data, so that you cannot recover those information in the decoder. So your loss function will be high. So the practical way is that you try different hidden neurons in the hidden data. Okay, you start from a very high or very low number of neurons in the hidden data, and you can observe what is the loss right now if I use 3 dimensions or 4 or 5 as the number of hidden neurons. So basically, it's a try and error. So you have a 1000 dimension in the original space. Maybe you can try, okay, I start from 500 hidden neurons, 200 hidden neurons, 100 hidden neurons, or 50 hidden neurons. You can take a look at the loss value. Okay, the more hidden neurons you use, the less loss function value it should be. 中文讲，如果你中间选的 hidden layer 的hidden neuron 的数量越多的话，那按理说这些 hidden neuron 是应该保留更多的 original space 里面的，就可以往右传，对不对？所以你中的 hidden layer hidden neurons 越多，你的 loss function 的值loss function value 应该就要越低嘛，因为它的还原效果越好，对不对？那但是你中间的 hidden neurons 选择的越少，那中间能够那是空间嘛，那个空间能够容纳原本的点到新空间里面，那就会显然就变成说它不太够。不太够的意思就是说，原本的旧空间里面的2个点原本是分开的，可在新空间里面，它们可能不小心叠在一起了，因为你的空间太挤， 然后就导致于这个点在 lens space 的时候太挤在一起，甚至叠在一起，那它几乎就无法还原到原本的那个explore 就新空间，好吗？所以选择这个不容易，就是最好的就是尝试啊，你比如说你有原本1000维，你可以试试看中间是500维、200维、100维、80、50维的时候，你的资料是不是所谓的information 的保留的程度是不是还是够好？那这是跟你的 loss function，loss 值越低，表示你保留的越好，loss 值越高。那当然这是一个 trade off， 对，你想要享受 dimension 缩减的好处，你就要丢掉一点点的 information， 对不对 ？Okay, so basically that is Autoencoder. Okay, so let's take a look at some figure right here. So I believe you have tried MLST at home, right? You have a handwriting digital handwriting data like this, right? The left-hand side. So the original inputs like this, and it should be 28 by 28 pixel, right? Pixels. So original we have 784 dimensions because the digit is 28 by 28. So we can compress. For example, usually we can try 100 dimension right here, and we recover it to 708. So we have an encoder right here, we have an encoder right here, and the design of the encoder and decoder is not necessary to be only one layer. You can put multiple dense layers in the encoder. For example, we have 784, right? So here is the encoder. We shrink it, for example, 300, and we then shrink it to 100, and we shrink it to 50. So that you can see that this encoder, we have several different layers, and it gradually shrink the dimension from 784 to 300, 100. And then here is the decoder, okay? And you still have the original space right here, and then we have another structure like this. We gradually recover the data from the lens space. So maybe I should draw it this way, and here is the space, right? The red one is the information we want to use in other, right? So maybe that. So you can design your own encoder with different number of layers, different number of mirrors. It's up to you. So here's the so I believe I tried to explain all these things right here, right? This encoder has one layers right here, another layers right here, so you have two different weights, and here is the other weight, okay? And we minimize the same thing. However, there are several things we have to talk about before we continue next topic. So it is possible to design a lens space like means I have a larger lens space, for example, that's 100, 100, 300. It is possible, but sometimes it is meaningless, right? Because you map your data from a small space to a larger space. Generally, you don't do so because you don't need such kind of things to add more complexity to your data. Okay, so usually we don't do so, but you can do that. You can represent your data by even use more and more dimensions, but usually you don't do so. The other one is like I have several dimensions, and as we mentioned before, usually we will have an activation function at each layer. Remove activation. I mean, usually you have to design an activation function at the end of each layer. However, you can manually remove it, or you can choose not to use any activation function, or you can manually choose I use activation function like this, which is linear. Okay, which means you don't change the relationship by using activation function, or your activation function is purely linear. That is quite easy to understand because the neural network is like computation of vectors, right? So basically, we have weights right here. We have different weights right here. So basically, x prime is right times 1, and that again weight 2, okay, and times weight 3, a 3. Weight 4. Okay, that's it. Alright. Think about one thing. If we remove all the activation function at each layer, or the activation function we choose right here is purely linear function, it likes we don't need it, we don't need it, and we don't. And it becomes very dangerous because it becomes weight 4, weight 3, 2, 1, and x. It becomes very dangerous because you describe a relationship between x and s prime by using a simple linear way, so that does not work. It does not work. OK， 我们中文再讲一遍哈。我们在做这个 neural network 的时候，为什么 activation function 这么重要？原因是因为它提供一个 non-linear 的 relationship between 你左边的 layer 跟右边的 layer， 对不对？好，那 Auto Encoder 这边会有个小小的问题，就是不要太自作聪明哈。就是如果你选择 activation function 是纯线性的，或是你就选择不使用 activation function， 这整个 neural network 会变得非常奇怪，就是它会变成纯粹的 weight 相乘，然后跟你的 x， 然后形成这个 s prime， 或者是 y or y， 或者是这个 y。那就表示你是在一个纯线性的方式描述 x prime 跟 x 之间的关系，或是 x 跟 y 之间的关系。这样会导致你的 neural network 会没有任何的用途，因为我们知道纯线性的函数是可以彼此互相叠加的嘛，对不对？什么意思呢？比如说，大家应该知道那个数学公式啊，我们数学公式那个矩阵的公式不是这样吗？如果我们的矩阵是1乘3的，然后再乘上3乘5的，再乘上5乘7的，它最后变成1，因为你直接把前面的位的做一个综合之后，它会变成它实际上可以变成一个更奇怪的位，然后再乘上 x， 然后等于你的 x prime， 或者是等于你的 y。因为乘法跟加法都是有结合律的，所以如果中间没有任何非线性的东西的话，你可以直接先把前面的位全部结合跟加起来，它就会变成单一的位在描述 x 跟 x prime 是 x 跟 y 之间的关系，这样会非常非常的危险，因为那就等于说你设计了5层、10层的 neuron 的 hidden layer 一点用都没有，因为它可以完全被单层的 neuron。对吧？乘法跟加法都刚好有结合律跟结合律的事情，所以这样是不好的。好，这不是有 Auto Encoder 啊，在所有的 neural network 都是这样的。所以 activation function 就至关的重要。这个我们下一下，好吗？好 ，OK， I think we can stop right here. Basically, we can find a lot of different implementation of Auto Encoder. So I provide several different of them. So you may take a look at. I believe I explained all the things right here. Okay. But if you need codes, okay, try to read those codes, okay, right here, okay, and I will talk about more things about Auto. And of course, we have several different codes right here. For example, you can simply click the TensorFlow 2.0, and here is the code provided by someone, okay. Here, it's the writer provides some very useful codes. So take a look at this code, and basically, I believe you can understand what the code try to explain. Okay, basically they are simply just the different version of layer stacking to represent encoder or decoder. Okay, of course you can use convolution layer, you can use max flow layer in your encoder.